Hey everyone, and welcome. Today we are diving into a concept that's honestly at the heart of everything from the battery in your phone to a massive bolt of lightning. It's called electrostatic potential. Now I know, it sounds a little intimidating, but stick with me. By the end of this, you're going to see it's actually a really elegant way to understand the invisible world of energy all around us. So let's jump right in. So let me start with a question for you. What on earth could possibly connect a simple, stretched-out spring with the incredible, chaotic power of a lightning strike? I mean, one is something you can literally feel in your hands. The other is one of nature's most spectacular and powerful events. But believe it or not, there's a deep physical connection between them.
And that connection, it all comes down to one thing: potential energy. Think about it. When you stretch that spring, or when charges separate inside a thundercloud, you are doing work against a force. And that work you put in, it doesn't just disappear. It gets stored, locked away as energy, just waiting for a chance to be released. This idea of stored work is the master key to this whole topic.
All right, so here's our game plan for today. We're going to build this idea up, block by block. First, we'll get our feet wet with the basics. Work, energy, forces, stuff we can easily picture. Then we'll take that knowledge and step into the electric world. From there, we'll hit the really big idea, the concept of potential itself. We'll see how it works for different charges, and finally, we'll figure out how to visualize these incredible invisible energy fields.
Okay, first up, the foundation. Before we can even begin to talk about electricity, we've got to be super clear on what we mean when we say we're storing energy by working against a force. Just imagine lifting a heavy book off the floor. You're fighting against gravity, right? You're doing work, and that effort isn't lost. It's now stored in the book as potential energy.
So what's really going on here? Well, potential energy is basically stored work. But it only applies to certain forces, these special conservative forces, like gravity or the force from a spring. What makes them so special is that it doesn't matter how you move the object. The energy you store only depends on where you start and where you finish. The path you take is totally irrelevant, which is a super powerful idea.
And this is where it gets really cool. If you look at the formula for gravity and the formula for the electrostatic force, the Coulomb force, they look like twins. They both depend on a fundamental property, either mass or charge, and they both follow the exact same inverse square law. They get weaker with the square of the distance. This is amazing for us, because it means all the logic we just used for gravitational potential energy, we can apply it directly to electricity.
So, let's take that logic and make the leap. We're now entering the electric world. And we're going to talk about a new kind of potential energy, electrostatic potential energy, which we give the symbol U.
The idea is exactly the same as lifting that book. Electrostatic potential energy, U, is simply the work you have to do to move a charge, which we'll call Q, against an electric field. So picture two positive charges. They want to fly apart, right? They repel each other. So if you want to push them closer together, you have to fight that repulsion. You have to do work. That work gets stored as potential energy, U. And notice, this is important, that amount of energy, U, depends on the size of the charge Q that you decided to move.
And just like with gravity, the electrostatic force is conservative. This is what makes potential energy such a useful concept in the first place. The work you do only depends on your starting point and your ending point. It doesn't matter if you take a direct route or some wild, loopy, scenic route to move your charge. The change in potential energy is precisely the same.
Okay, deep breath. We're at the big idea now. This is probably the most important conceptual jump we're going to make. We're about to go from potential energy, U, which is tied to a specific charge, to something way more fundamental, something we just call potential.
Here's the question that gets us there. Potential energy, U, is great, but it always describes an interaction between a field and a specific charge you're moving. But what if we wanted to describe the energy landscape of the space itself? Create a kind of energy map of an area that's valid no matter what charge we eventually decide to place there.
And the solution is just so elegant. We invent a new quantity, electrostatic potential, V. And we define it by simply taking the potential energy, U, and dividing out the charge, Q. By doing that, we've basically factored out the influence of our specific test charge. What's left, V, is a property of the space itself. It's the potential energy per unit of charge. We've made our energy map, and the unit we use to measure it, that's the volt.
So now we've got this really powerful new concept, V. Let's take it for a spin. Let's see what this potential looks like for a couple of really common situations, a single-point charge and something called an electric dipole.
For a single, lonely point charge, the potential V is beautifully simple. It just drops off smoothly as 1 over the distance, r. The best way to picture it is to think of a positive charge as creating a kind of energy hill around itself. The potential V is like the altitude on that hill. It's highest at the center, and it gets lower and lower as you move away.
Now, an electric dipole, that's just a positive and a negative charge sitting close together, is a whole different story. Here, the potential drops off way faster as 1 over r squared. And there's another twist. It also depends on the angle you approach from. So our energy landscape isn't a nice symmetrical hill anymore. It's a much more complex shape, with hills and valleys that change depending on your direction. Let's just put these side by side because the differences are really telling. For distance, the point charge's potential fades gently as 1 over r. The dipole's potential plummets as 1 over r squared. Direction, the point charge doesn't care, it's totally symmetrical. The dipole absolutely cares about the angle. But look at this last one. Where is the potential 0? For a point charge, it's only 0 when you're infinitely far away. For a dipole, it's also 0 on the entire flat plane that slices right between the two charges. Kind of cool, right?
Okay, so we've established that potential creates this invisible energy landscape in space. But how in the world do we actually visualize something we can't see? Well, we have a fantastic tool for that, and it's called an equipotential surface.
You know how on a topographical map of a mountain you have all those contour lines, and every point on a single line is at the exact same elevation? An equipotential surface is exactly that, but for electrical potential. It's a surface where every single point has the same voltage. And what that means is if you move a charge anywhere along that surface, you're not going uphill or downhill. It takes 0 work. And these surfaces form some really neat, predictable shapes. For that single point charge, the equipotentials are just a set of perfect concentric spheres. For a dipole, they look more like ovals that are squeezed in between the two charges. And if you have two positive charges near each other, the surfaces eventually merge and wrap around both in this kind of peanut shape. And here's the final rule that locks it all together. The electric field lines, the arrows that show you which way a positive charge would be pushed, are always perpendicular to these equipotential surfaces. Go back to that mountain map. What's the fastest way down? It's a straight line that cuts across the contour lines at a right angle, right? It's the same thing here. The electric field always points in the direction of the steepest drop in potential. So let's just quickly retrace our steps. We started with a comfortable idea, potential energy, U, which is just stored work. Then, to make it more universal, we cooked up potential, V, by basically dividing out the charge. That gave us a property of space itself, our energy map. And finally, we learned how to draw that map using equipotential surfaces, the contour lines of the electric world. So we've built this amazing toolkit. We can now describe and visualize the energy that's stored in an invisible electric field. Which, of course, leads to the next big question. If we understand this energy landscape so well, how could we actually design a device specifically to store that energy? How would we build something to hold it? Well, that is a fantastic question for another explainer. Thanks for tuning in.